dissociation equations. This is helpful in terms of determining how we're going to use reference table F, which determines if something will be soluble or not. So when we put an ionic compound into water, it breaks apart into its component ions. A very simple example of this is NaCl. So we have one Na and one Cl. Those are the two ions making up that compound. You can easily look up their charges, the periodic table, and we write a plus sign between them showing that they have dissociated or broke apart. Anything that is on reference table E stays intact with one another because, for example, if you look at SO4, there are actually covalent bonds between the S and the O. So those are not going to dissociate in solution. However, this compound still will dissociate. There's an ionic bond right there. So what's going to happen for calcium sulfate? This is going to break into calcium, which has a +2 charge, and a sulfate ion, that's -2 charge. You do need to make sure that you're writing your ions with proper charges, showing that plus sign in between them so that we know that they dissociated. So you are going to have to use your periodic table and reference table E. It's very important also to understand the number of ions that are produced, so that can be really important in certain types of questions we're going to answer. So CaBr2 is actually going to break down to give us 1 Ca, 2 right here, again that's got a +2 charge, tells us that we're going to have 2 bromines. We actually bring that out front and make that a big 2, so that'll look like that. And it's nice to be able to actually determine now how many types of, or how many ions that produce for us. So when we put in 1 mole of calcium bromide, that actually produces 3 moles of ions. 1 mole of calcium ion, 2 moles of bromine ions. So in our next compound we have 3 potassiums. Potassium has a +1 charge. And remember PO4, that's reference table E, those are covalent bonds. So that's going to be PO4 with a -3 charge. Our next one, we have 2 aluminums, each one with a +3 charge. Then we have 3 carbonate atoms, each one with a -2 charge. And again, conductivity and something else we're going to talk about having to do with freezing point depressions. It is going to come into play, so it's important to understand that the number of ions in solution will affect things like conductivity. So if we were to put 1 mole of each of these substances into water, knowing the amount of ions that come out will let us know, how much conductivity we had. There may be an error in your packet where there's a 2 right there. That should be a 3. So if you have that error, please change that to a 3. So sodium chloride, as we mentioned, give us NAs and Cls. This produced 2 moles of ions. So 1 mole of NaCl produces 2 moles of ions. 1 mole of Na3PO4 will produce 3 sodiums and 1 phosphate, which is a total of 4 moles of ions. NaOH will break into Na plus and OH minuses. That's 2 moles of ions again. And sodium sulfate will give us 2 sodiums and 1 sulfate, which is a total of 3 moles of ions. So if we wanted to know which one of these is going to have the greatest conductivity, it would be the one that would produce the most moles of ion per mole of the solid we put in, which would be sodium phosphate. There is a lead precipitate demo that we're doing in class. So in order to determine how this proceeds, we had to break these down into ions. So we reacted these actually happens, these ions that we create by dissociation all float around freely in solution and end up making a nice double replacement reaction. These are each aqueous solutions that we mixed. And we get to see this nice precipitate that forms. So we have these two new compounds that form due to a double replacement reaction. So all those associated ions up there kind of do a little square dance here. And what happens is lead and potassium essentially are able to switch places in these compounds. We get potassium nitrate and lead iodine. Now, we started with two aqueous solutions, and at the end we're actually going to have a solid that forms. So we can actually use table F to determine which of these is that solid. So if you go to reference table F, we're going to look up first our potassium nitrate. Potassium is from group 1. Things from group 1 are almost always soluble, pretty much always soluble. So that kind of rules out the KNO3, that's still an aqueous solution. If we have something with iodine and it bonds with lead, it's an exception to that rule and actually is an insoluble compound. So we're actually going to see a precipitate in this reaction that hopefully you'll be able to see in class, where we're going to form a solid, and this guy remains as an aqueous solution. You have to balance this guy, so I'm going to stick a little 3 there, and stick a little 3 there. So next, we'll get into talking about how to read reference table